Last time, we discovered that every binary search is really about one thing: finding the boundary where a monotonic predicate flips from 0 to 1. But this framework extends far beyond arrays. Welcome back to farmerboy's channel. Let's see where it takes us. The general problem is find where a function crosses a threshold in some interval. Our concrete example: find the square root of 49. The x where x squared hits 49. Let's plot x squared from 0 to 12. Our target is 49 and the curve crosses right here at 7. Think of it this way: for every x, either x squared is below 49 or is at least 49, a predicate that flips from false to true. But there are infinitely many numbers between 0 and 12. We can see the answer on the graph, but a computer cannot look. It can only test one value at a time, and it will never land on 7 exactly by guessing. Same pattern we saw earlier, a boundary that splits the domain into false and true. Now we just need to find it. Let's find it. Interval 0 to 12. Mid is 6. Is 6 squared at least 49? 36. Not enough. So we set L to 6. Notice that it's not mid plus 1. On real numbers, there's no next value. The interval just strings smoothly. Mid is 9. Square is 81. Above. R becomes 9. Same thing. R equals mid, not mid minus 1. Mid is 7.5. Square is 56. Still above. R becomes 7.5. Mid 6.75. Square is 45. Below. L becomes 6.75. Mid 7.125. Square is 50. Just above. R becomes 7.125. Watch it closing on 7 from both sides. A few more iterations and the gap is tiny now. It's closing in on 7, but it will never hit it exactly. So when do we stop? And there's a practical reason it can never collapse. Computers store real numbers with limited precision, floating point. There are tiny gaps between representable values. The interval can never truly shrink to a single point. So we pick a precision epsilon. We stop when the interval is smaller than epsilon. In discrete search, we stop when left crosses right, a clear endpoint. Here we declare upfront how close is close enough. For a double, epsilon of 10 to the minus 9 gives us about as much precision as the machine can handle. Same predicate framework. Define f of x. Is x squared at least 49? Left of the answer, or zeros? Right of the answer, or ones? The boundary is just a real number now, not an index. How many iterations? Log base 2 of the interval divided by epsilon. For a range of 0 to a billion with a precision 1 billionth. About 60 iterations. That's it. Here's the code. Notice no plus 1, no minus 1. Just L equals mid or R equals mid. The loop strings the interval until it's smaller than epsilon. There's a whole class of problems that don't give you anything to search through. Let's try one. Koko has piles of bananas, 3, 6, 7, and 11. Each hour she picks a pile and eats k bananas from it. If the pile has fewer than k left, she finishes it. But the hour is still used up. Guards return in 8 hours. Find the minimum k. Let's see what happens at speed 2. Pile of 3, eat 2. Then the last one, that still takes a full hour. 2 hours. Pile of 6, 3 hours. Pile of 7, 4 hours. That last banana still costs a full hour. Pile of 11, 6 hours. Total 2 plus 3 plus 4 plus 6, 15 hours. Way too slow. Guards come back in 8. So each pile takes ceiling of pile size over k hours. Any leftover still costs a full hour. And since each pile's time depends only on its own size and k, the order she eats them doesn't matter. the total is always the same, so k equals 2 doesn't work. What speed do we need? We could try every value, or we could be smarter. K equals 2 doesn't work. K equals 1, even slower, definitely not. But if some speed k does work, then k plus 1 is faster. It can only take less time, also works. That's monotonic. There's the boundary. Below it, too slow. At or above, fast enough. We can binary search for it. The answer space, L is 1, R is 11, the largest pile. At speed 11, every pile finishes in 1 hour. Let's find the boundary. Binary search on the answer. Mid is 6, total hours at speed 6. Ceiling 3 over 6 is 1, 6 over 6 is 1, 7 over 6 is 2, 11 over 6 is 2, total 6, feasible, go left. Mid is 3, ceiling 1 plus 2 plus 3 plus 4, that's 10, too slow, go right. Mid is 4, 1 plus 2 plus 2 plus 3, 8, just feasible, go left. L is now greater than R, converge. L lands right on the boundary. The first value where the predicate is true, that's our minimum speed, 4. R starts at the largest pile, that's our answer space. The predicate checks feasibility, sum up ceiling divisions, compared to H. The search loop, same template. Complexity, log of the answer range iterations, each checking n piles, all of n log max, constant space. Problem 2. Ship packages. Weights 1 through 10, shipped in order. Each day you load consecutive packages until the next one would exceed capacity. Find the minimum capacity to ship everything in 5 days. Let's try capacity 12. Load packages into the ship one by one until the next won't fit. Day 1, 1, 2, 3, 4, total 10. Adding 5 would exceed 12. Start new day. Keep going. 6 days, too many. Same logic. If capacity X works, anything bigger also works. Monotonic. Answer space. L is 10, must carry the heaviest package. R is 55, total weight. Ship everything in 1 day. Mid is 32. Loading. Day 1 takes 1 through 7, weight 28. Day 2, 8, 9, 10, just 2 days, go left. Mid 20, 4 days, feasible, go left. Mid 14, 6 days, too many, go right. Mid 17, 4 days, feasible, go left. Mid 15, 5 days exactly, feasible, go left. L is greater than R, converge. Minimum capacity 15. Same pattern. L lands on the battery, answer 15. Same structure. The predicate simulates the loading process. Bounds. L is the heaviest package. R is the total. Same search loop. Only the predicate changes. All of n log the range. Constant space. Binary search isn't just for coding problems. It's built into tools you already use. Here's one. You are working on a project. The latest version has a bug, but it worked fine 2 weeks ago. Somewhere in those 8 commits, something broke. Git bisect does binary search. Test the middle. Commit 4. Good. Test 6. Bad. Test 5. Bad. Commit 4 was good. 5 is bad. Found it. 3 tests instead of 7. See the predicate? Does this commit have the bug? Monotonic. Once it's broken, it stays broken. The binary is the first bad commit. In practice, you just tell Git, this is bad, that was good. It does the binary search for you. Second application, databases. When you query a table with millions of rows, how does it find your record instantly? B-tree indices. Finding key 42. 3 levels, 3 decisions, done. Here's where binary search lives. At every node, the keys are sorted. We binary search them to pick the right child. It's binary search inside binary search. A million rows? About 20 node visits. That's why your database queries return in milliseconds. Binary search is not about arrays. It's about finding a boundary in any monotonic space. Arrays, real numbers, answer spaces, commit histories, tree structures, all the same idea. One loop, one predicate, one boundary. Thank you so much for watching. If you find this useful, like, subscribe, and press the notification bell to not miss any new update. I'll see you in the next videos.